So whenever you want to train a machine learning model, your model needs to represent data in some way. Now, we need the model to represent the data in some sort of numerical fashion, and we'll talk about why this is in later videos with gradient descent and how the algorithm is actually working. But what you need to understand is that if you were training your model using data, it needs to be in the form of numbers. You can't have an MP3 file or PNG file fed directly into the model. That won't work. So, how do we do this? How do we sort of encapsulate our data in a set of numbers? Well, luckily for us, there's a section of mathematics called linear algebra, which very, very generally speaking is the study of these mathematical objects called tensors. And as you can guess, given the fact that Google's sort of flagship API is called TensorFlow, you can imagine that tensors are of great importance to machine learning. And this is true. So this is neat and all, but what exactly is a tensor? That's what this video is going to cover. You can think of a tensor as sort of an ordered series of numbers, and that those numbers have a sort of structure, and there are different kinds of tensors, each with a rank, and that there's a nice geometric interpretation for tensors. So we're going to start with the simplest of tensors, a rank 0 tensor called a scalar. Now a scalar is just one number. It's just a number. It could represent many things: temperature, distance, speed. It is a number. So this is the most basic, and it has a rank 0. So that's interesting. And the sort of geometric interpretation is you think of this number as a cube. And then the way you remember its rank is imagine that a point in space is 0 dimensions, right? That is a 0-dimensional point. Well, similarly, we'll get into why this analogy works with this, but just how there's just sort of one value of where a point is located, there's one value stored in the scalar. So our rank 1 tensor is the most common type of tensor to be inputted, and this is a vector, as it's also called. This is a rank 1 tensor, and you may have seen it represented in other classes such as physics as perhaps a column or a row vector. It just holds various numbers. And while there is a nice geometric interpretation as to what this means, we won't be covering the sort of arrows and all that. That'll be in a separate video. We'll talk about that. But the importance is that you can think of a vector as kind of analogous to a line. Just as a vector has one rank, a line has a dimension 1. And so there are several possible values, on a line, different values stored on here, just as there are several numbers in a vector. And, vector could represent velocity, acceleration, there's all these physics applications, but it could also represent various pieces of data about someone that will assess whether or not they're at risk for a heart attack, or whether they'll default on a loan, let's say. Very interesting stuff you can do with this, and this is very common sort of input. And you see it's several of these cubes lined up, several numbers in a structured manner. Now you also notice that here the amount of numbers, the number of blocks, we call the dimension of the vector. Now a lot of people use rank and dimension sort of interchangeably, and I think that's a big mistake. And the reason for that is because rank is specifically talking about the sort of dimensions of the actual shape of the tensor, right? If you have a rank 4 tensor, rank 3 tensor we'll look at, you know the general shape of the tensor, but the dimensions tell you the length or how many pieces of data you have. And this will all make sense soon. But just keep in mind that dimensions is talking about the amount of data in each sort of, line here, while rank is talking about how many different ways you can look at this data. We'll see here, we have a matrix right here. Matrix is a rank 2 tensor. This is analogous to a plane, which is 2 dimensions. You can see it's sort of flat. You have many different pieces of data on here. We have several vectors, right? And the thing to note is that if you have a rank n tensor, where n is greater than 1, the rank n tensor you can view as kind of being made up of rank n minus 1 tensors. So here, A rank 1 tensor is really just a bunch of rank 0 tensors. A rank 2 tensor is like a bunch of rank 1 tensors sort of stacked on top of each other. And this is a pretty important idea. So here we have this sort of plane of blocks, sort of wall of numbers here, if you will. We call this a matrix. And here we would have two separate dimensions. We have a dimension here, we have a dimension going along here. So just keep that in mind. And finally, here we have a rank 3 tensor. Now this doesn't have a special name, it's just called a rank 3 tensor. And any tensor of a greater rank also doesn't have a special name. So rank 4 tensor, not a special name associated with it, it's just a rank 4 tensor. So here we kind of have this cube of numbers, or if you have different dimensions, maybe a rectangular prism of numbers. And this could represent colored photos where you have each little slice here could represent one image of the different RGB values, you know what I'm saying? And it's a way of looking at it, it's a way of storing data in a sort of cube of numbers. And it has some structure to it, and as you can imagine, this is analogous to a three-dimensional space. So we have these three ranks going on here. So, as again, this is made up of rank 2 tensors, so you could imagine that a rank 4 tensor might look something like this. It's several rank 3 tensors sort of arranged in this way. Kind of like that, right? And a rank 5 tensor, you would just add more and more of these. But this idea is kind of important for how we index them. Now you may have noticed that in programming, the tensors are very similar to lists or arrays in the sense that they hold values in a sort of structured way, an ordered sequential manner. And you can also have, this would be like a 2-dimensional array or a 3-dimensional array right here. And you index them just the same way. So if you wanted to index a vector, you say you want its the vector A, you want its second value, you just put A, you put a subscript 2. Kind of like this. Here, if you want to index a matrix, you would index row and then column. So if we wanted to talk about this point right here, we would subscript 2, kind of like that. And unlike in programming, you don't start at 0, or at least most of the time you don't start at 0. You usually do 1 indexing. And so these are sort of the main points of tensors. A lot of people like to complicate them and give these sort of weird geometric interpretations of them. Really, you can just think of tensors as arrays or as these structured ways of holding data in these sort of rectangle, cube shapes. That's really all you need to understand about tensors. This is generally how you represent data as well. It's very important. But now we're going to be talking about the more interesting parts of machine learning coming up.